Out in the deep universe, motion is constant, yet almost nothing ever touches. Entire galaxies drift through space at hundreds of kilometers per second, guided by gravity across distances so large they resist intuition. Over billions of years, these vast systems slowly approach one another, their shapes stretching, their stars rearranging, their futures quietly rewritten. From a distance, the event looks dramatic. Spirals twist. Long streams of light arc outward. Two luminous forms seem destined to crash. But up close, something unexpected happens. Stars pass by stars without contact. Planetary systems remain intact. No great wave of destruction sweeps outward. What unfolds instead is a long, gentle reshaping of structure, driven not by impact but by gravity acting patiently over time. A collision that is not a crash. A merger that unfolds in near silence. This is one of the strangest truths in astronomy. The largest collisions in the universe are also some of the calmest. They take place in near vacuum, stretched across timescales far longer than any civilization, any species, or any single star could experience directly. From within a galaxy, the night sky would change so slowly it might never feel like an event at all. Tonight, the focus is not on explosions or chaos, but on scale, emptiness, and motion, on how structure evolves when almost everything is space, on how the universe transforms itself without force, without noise, and without anything ever really touching. Welcome to The Sleepy Scientist. If this kind of calm, factual exploration helps you unwind, consider liking the video and subscribing to the channel. And as galaxies quietly pass through one another across the universe, feel free to share where you're watching or listening from, wherever you happen to be drifting tonight. A collision is usually imagined as a moment of contact. Two cars meet at a junction. A ball strikes a wall. Something moving encounters something solid, and the result is noise, force, and sudden change. In everyday life, collisions are sharp events. They happen quickly. They leave marks. They are defined by impact. That expectation follows naturally from life on Earth, where matter is dense and distances are small. Rooms have walls, roads have edges, objects tend to be close together. An empty space is something that exists only briefly between one surface and the next. In that setting, a collision without contact sounds like a contradiction, almost a trick of language. Out in the universe, the same word means something very different. At cosmic scales, a collision does not need contact. It does not require surfaces to meet or objects to strike one another. Instead, it describes a long process of interaction, guided almost entirely by gravity, unfolding across distances so large that impact becomes almost irrelevant. When astronomers speak about galaxies colliding, they are not describing a crash in the everyday sense. They're describing two vast systems passing through the same region of space and slowly reshaping each other as they do. The key to understanding this difference lies in emptiness. A galaxy appears solid in photographs. Its spirals glow. Its core shines brightly. From a distance, it looks like a crowded, luminous structure packed with stars, but their appearance is deceptive. A galaxy is not a solid object. It is a gravitational system, held together by mass and motion, in which almost all of the volume is empty space. Consider a single star system like the one surrounding the Sun. The Sun itself occupies a region a little over 1 million kilometers across. The nearest planet orbits tens of millions of kilometers away. Beyond that, the outer planets drift billions of kilometers from the center. Even within this small corner of the galaxy, space dominates. If the Sun were reduced to the size of a grain of sand, Earth would orbit several meters away, and the nearest star would be thousands of kilometers distant. That pattern repeats on larger scales. Stars within a galaxy are separated not by meters or kilometers, but by distances measured in light years. Even in relatively dense regions, the typical separation between stars is vast. There are places where stars cluster more tightly, such as globular clusters, yet even there, collisions between stars are rare over the lifetime of the universe. This is why the phrase "without touching" is not poetic language, it is a literal description. When two galaxies approach each other, their stars do not behave like particles in a collision chamber. They do not slam together or shatter. Instead, they continue along their paths, guided by gravity, slipping past one another with enormous distances still separating them. The probability of one star directly striking another during a galactic merger is so small that for most purposes it can be treated as zero. This idea was unsettling even to early astronomers. When galaxies were first recognized as systems beyond the Milky Way, there was a natural tendency to imagine them as enormous star clouds that would collide violently if they met. Over time, careful observation and theoretical work showed otherwise. The universe, it turned out, is far emptier than intuition suggests. Gravity changes everything. A galaxy is not held together because its stars are close. It is held together because gravity acts across distance. Every star, every cloud of gas, every grain of dust contributes to a gravitational field that extends far beyond what can be seen. This means that two galaxies can begin influencing each other long before they appear to meet. Their shapes stretch, their motions shift. Long streams of stars can be pulled outward into space, tracing arcs that last for hundreds of millions of years. None of this requires contact. Instead of impact, the dominant process is interaction. Orbits change. Paths bend. Energy is redistributed slowly and gently. The changes are real, but they are gradual, unfolding over spans of time that make sudden violence impossible. To anchor this in scale, it helps to step back even further. A typical galaxy contains hundreds of billions of stars, yet the combined volume of all those stars occupies only a tiny fraction of the galaxy's total size. If all the stars in a galaxy were compressed together, the resulting object would still be minuscule compared to the space the galaxy normally fills. Most of a galaxy is simply room for motion. This is why two galaxies can pass through each other and remain recognizably intact for long periods. Their stars weave through overlapping gravitational fields, like two swarms of insects crossing paths in open air. The swarms influence each other's motion, but individual members rarely collide. There is quiet humor hidden in this idea. The largest structures in the universe participate in collisions that are defined by not touching. The word remains the same, but the meaning shifts entirely. What feels contradictory at human scale becomes inevitable at cosmic scale. Scientific bodies such as space agencies and observatories have confirmed this picture repeatedly, through observation and simulation. Detailed computer models, built using the laws of gravity and informed by telescope data, show galaxies approaching, overlapping, and merging without widespread stellar destruction. These simulations match what is seen in real systems scattered across the observable universe. The long tails, warped shapes, and stretched arms tell the same story again and again. Even the word empty needs care here. Space is not nothing. It contains gas, dust, radiation, and unseen mass that reveals itself only through gravitational effects. But compared to the density of everyday objects, it is astonishingly sparse. This sparseness is what allows motion without impact, change without collision in the usual sense. Thinking this way requires letting go of familiar instincts. The mind expects collision to involve contact, because that is how the world behaves at human scale. At galactic scale, those instincts mislead. The universe operates under the same physical laws everywhere, but the outcomes look different when distances stretch and densities fall. Once this shift in perspective settles in, the phrase, "when galaxies collide without touching," stops sounding strange. It becomes a precise description of a process shaped by scale, probability and gravity rather than forceful impact. It describes a universe where interaction is subtle, patient and continuous, where enormous changes arise not from crashes but from slow rearrangements of motion. This reframing matters because it clears away misconceptions before anything more detailed is explored. Without it, later descriptions of mergers, star formation, and structural change would seem contradictory or incomplete. With it, the story of galactic interaction becomes coherent, grounded, and surprisingly calm. The universe is not built from constant collisions. It is built from motion through space that is mostly empty, guided by gravity acting quietly across immense distances. Understanding that simple fact reshapes how everything else is seen, from the movement of stars to the evolution of galaxies themselves. To understand what happens when galaxies interact, it helps to pause and ask a quieter question first. What is a galaxy, really, when stripped of its glow and its familiar shapes? What is actually there, moving through space, responding to gravity, and slowly changing over time? A galaxy is not a single object. It is a layered system, built from several very different ingredients, each behaving in its own way. Together, they form a structure that can be stable for billions of years, yet flexible enough to be reshaped by encounters with others like it. The most obvious component is stars. These are the parts that dominate photographs and capture attention. Hundreds of billions of stars can orbit within a single large galaxy, each producing light through nuclear fusion at its core. Stars give galaxies their color, their spiral arms, and their bright central regions. They also provide the reference points by which galaxies are classified and compared. Yet stars, for all their brilliance, are not the bulk of a galaxy in either volume or mass. They are bright markers embedded in something much larger and far more diffuse. Between the stars lies gas. This gas is mostly hydrogen, with smaller amounts of helium and trace elements forged inside previous generations of stars. In some regions it is cold and thin, drifting quietly through interstellar space. In others it is compressed and heated, glowing faintly or collapsing to form new stars. Gas is the raw material of future stellar generations, and it plays a central role in how galaxies change over time. Mixed into this gas is dust. Despite the name, cosmic dust is not like household dust. It consists of tiny solid grains made of carbon, silicon, oxygen, and heavier elements. These grains absorb and scatter light, shaping how galaxies appear when observed. Dust lanes trace spiral arms. Dust clouds obscure stellar nurseries. Although dust contributes very little mass, it has an outsized effect on appearance and behavior. Together, stars, gas, and dust make up what is often called the visible galaxy. This is the part that telescopes detect directly. It is also the part that feels most tangible. But even combined, these components account for only a fraction of what a galaxy truly contains. The largest contributor to a galaxy's mass is something that cannot be seen at all. Dark matter does not emit light, absorb light, or reflect light. Its presence is known only through its gravitational influence. When astronomers measure how fast stars orbit within galaxies, or how galaxies move within clusters, the visible matter is not enough to explain the motion. Something else must be there, providing additional gravity. This unseen component forms an enormous halo around each galaxy, extending far beyond the visible stars and gas. The dark matter halo acts like a scaffold, shaping how galaxies form and how they hold together. Without it, galaxies as they are observed could not exist. With it, their motions make sense. The exact nature of dark matter remains unknown, but its role in galactic structure is well established. In terms of mass, it outweighs stars and gas by a wide margin. Most of what a galaxy is made of never appears in images at all. At the centre of many galaxies lies another remarkable feature, a supermassive black hole. These objects contain millions or billions of times the mass of the Sun, compressed into a region smaller than a planetary system. Despite their reputation, they do not act like cosmic vacuum cleaners. Their influence is strongest nearby, shaping the motion of stars and gas close to the core. Central black holes are linked to the evolution of their host galaxies in subtle ways. As gas falls inward, energy is released. Jets and radiation can affect star formation across large regions. Although the black hole contributes little to the overall mass compared to dark matter, it plays a key role in regulating activity at the galaxy's heart. When all these pieces are considered together, a galaxy becomes something very different from a glowing object drifting through space. It is a dynamic system. Light marks only a small fraction of what is present. Gravity binds everything together, extending far beyond what the eye can see. This understanding helps explain why galaxies come in different shapes. Spiral galaxies, with their winding arms and rotating disks, are often rich in gas and actively forming new stars. Their structure reflects a history of relatively gentle interactions and sustained rotation. Elliptical galaxies, by contrast, are smoother and rounder, with stars moving in more random orbits. They tend to contain less cold gas and show little new star formation. Irregular galaxies lack a clear shape altogether. They may be small, distorted or disrupted, often as a result of past interactions or ongoing gravitational influence from larger neighbours. These categories are not fixed identities. They are outcomes. A spiral galaxy can become an elliptical one. An irregular galaxy can settle into a more ordered form. The shape a galaxy has at any moment reflects its past, not a permanent label. Early in the 20th century, astronomers were only beginning to piece this together. Edwin Hubble played a major role by systematically observing and classifying galaxies based on their appearance. His work helped establish that galaxies are separate systems beyond the Milky Way, and that their shapes follow recognizable patterns. Hubble's classification scheme was never meant to suggest an evolutionary ladder, but it provided a useful language. Over time, as observations improved and theoretical understanding deepened, it became clear that interactions and mergers could move galaxies from one category to another. The shapes were snapshots, not destinies. One of the most counterintuitive aspects of all this is how little space stars actually occupy. Despite their numbers, stars are tiny compared to the distances between them. Even in a galaxy packed with hundreds of billions of stars, most of the volume is empty. The luminous parts are like scattered embers in a vast dark field. This is why a galaxy can be massive without being crowded. It is also why gravity, not contact, governs galactic behavior. Stars orbit within gravitational fields shaped largely by dark matter. Gas flows respond to pressure and attraction. Dust drifts and absorbs light. Black holes influence their surroundings quietly and persistently. Seen this way, a galaxy is less like a solid object and more like a slow-moving ecosystem. Matter circulates, energy flows, Structures form, dissolve, and reform over time. Light provides hints, but gravity tells the deeper story. Grounding the idea of a galaxy in this physical reality matters. Without it, interactions between galaxies seem confusing or contradictory. With it, those interactions become understandable consequences of how mass and space are arranged. What moves during a galactic encounter is not a solid body, but a layered system dominated by emptiness, guided by unseen mass, and marked by points of light that occupy only a tiny fraction of the whole. Once that picture settles in, the behavior of galaxies begins to feel less dramatic and more inevitable, shaped by structure rather than spectacle. A galaxy is not what it looks like at first glance. It is what holds together, what extends beyond sight, and what responds patiently to gravity over immense spans of time. The most important feature of a galaxy is not what shines, but what lies between the points of light. From Earth, the night sky gives the impression of closeness. Stars appear sprinkled across a dark surface, separated by tiny gaps. Constellations form shapes that feel compact and familiar. This impression is comforting, but it is deeply misleading. The true distances between stars are so large that the word gap barely applies. Take the nearest star beyond the Sun. Even our closest neighbour sits more than 4 light-years away. That distance is so large that light, moving faster than anything else in the universe, takes over 4 years to cross it. Nothing about everyday experience prepares the mind for separations like that. To make this easier to picture, imagine shrinking the Sun down to the size of a small marble. At that scale, Earth would orbit several meters away. The outer planets would be spread across a space the size of a neighborhood, and the nearest star would not be in the same city, or even the same country. It would be thousands of kilometers away. Between those two marbles there would be nothing at all. That emptiness is not an exception. It is the rule. Galaxies contain hundreds of billions of stars, yet they are spread across regions tens or hundreds of thousands of light-years wide. Even in the bright spiral arms where stars are more common, the average separation remains immense. Most of the volume of a galaxy is simply space where nothing solid exists. This is the key reason galaxies can pass through one another without stars colliding. When two galaxies overlap, their stars do not suddenly become crowded. They continue to occupy roughly the same relative distances they had before. The space between stars in one galaxy is still vast, and the stars from the other galaxy slip into those gaps with ease. It is not that collisions are rare, it is that they are almost unthinkable. The idea of a stellar collision sounds dramatic, but it is statistically negligible. Even during a direct galactic overlap, when billions of stars share the same region of space, the chance of one star striking another remains vanishingly small. Astronomers can run simulations that track millions of stellar paths during mergers and still find essentially no direct impacts. This comes down to simple probability, guided by separation and size. Stars are tiny compared to the distances between them. A typical star is a few million kilometers across. The space between stars is measured in trillions of kilometers. When objects are that small, relative to their spacing, direct contact becomes extraordinarily unlikely. It is the difference between throwing 2 handfuls of sand into the open ocean and expecting the grains to collide. Density matters here, but even the densest stellar environments remain mostly empty. Star clusters are often cited as crowded places, and in relative terms they are. In globular clusters, hundreds of thousands of stars can be packed into a region only a few dozen light-years across. Compared to the rest of a galaxy, this is dense. Compared to everyday standards, it is still almost entirely void. Even in these clusters, stars are typically separated by distances far greater than the size of their planetary systems. Collisions can happen there, but they are rare events spread across billions of years. They are notable precisely because they are exceptions. This helps explain why galaxy collisions do not produce chains of stellar impacts. When two galaxies merge, their densest regions overlap briefly, then drift apart again. The time spent in close proximity is short compared to the enormous distances involved. The stars simply do not have the opportunity to meet. There is a quiet irony in this. Galaxies are sometimes described as crowded cities of stars, yet they behave more like rural landscapes stretched across cosmic scales. Everything is connected by gravity, but nothing is close. The mind often tries to picture galactic overlap as two clouds of glowing matter slamming together. A more accurate image is two intricate lace patterns sliding through one another without tearing. The patterns distort, threads stretch, but the spaces between threads remain dominant. Astronomers have confirmed this picture by studying galaxies caught mid-merger. Long tidal tails stream outward. Spiral arms twist and warp, yet individual stars continue along smooth paths, largely unaffected by the presence of foreign neighbours. The violence is visual, not physical. Even when stars pass relatively close to one another, gravity softens the encounter. Their paths bend slightly, orbits shift, but contact remains unlikely. Space gives them room to miss. This vast emptiness also explains why planetary systems are generally safe during galactic mergers. Planets orbit stars on scales that are tiny compared to interstellar distances. As stars pass by other stars, those encounters are usually too distant to disrupt planetary motion. A solar system could travel through the heart of another galaxy and remain intact, unaware that anything unusual is happening beyond a slowly changing night sky. There is gentle humour in how counterintuitive this all feels. On Earth, more objects in one place means more collisions. In space, adding billions of stars barely changes the odds. Scale reverses expectation. Scientific institutions that model galactic evolution rely heavily on this emptiness. Their simulations assume that stars can be treated as points moving through a smooth gravitational field, rather than as objects that strike one another. When these models reproduce real galaxies with striking accuracy, it reinforces the same conclusion. The universe is sparse to a degree that defies instinct. Understanding this sparsity is essential. Without it, the calm nature of galactic mergers makes little sense. With it, the idea of galaxies interpenetrating becomes not just plausible, but inevitable. Galaxies are vast because space allows them to be. Their stars shine because they are isolated, separated, and stable. When galaxies meet, they do not become crowded. They remain what they always were, immense collections of light suspended in an ocean of emptiness. Once this is absorbed, the phrase "without touching" loses its mystery. It becomes a straightforward description of how nature behaves when distances grow large and matter grows rare. At these scales, space itself becomes the dominant feature, shaping everything that follows. If stars rarely touch and matter is spread so thinly, it raises a natural question. How can galaxies affect one another at all? What reaches across those immense gaps and produces the dramatic shapes seen in merging systems? The answer is gravity. Gravity does not require contact. It does not fade at the edge of an object. It extends outward endlessly, growing weaker with distance but never truly disappearing. In a universe where space dominates and matter is sparse, gravity becomes the primary way objects communicate. At everyday scales, gravity feels subtle. A falling object accelerates quietly toward the ground. The pull between two people standing side by side is real, but far too small to notice. At cosmic scales, however, gravity governs everything that moves. It shapes the paths of planets, the structure of stars, and the behavior of entire galaxies. The earliest clear description of gravity comes from Isaac Newton, who showed that every mass attracts every other mass. In Newton's picture, gravity acts instantaneously across space, pulling objects together in proportion to their mass and distance. This framework works remarkably well for understanding the motion of planets and stars, and it remains useful for many astronomical calculations. Centuries later, Albert Einstein refined this picture with the general theory of relativity. Instead of gravity being a force that reaches across space, Einstein described it as a curvature of space and time themselves. Mass tells space how to curve, and curved space tells matter how to move. The result is the same familiar attraction, but understood at a deeper level. For galaxies, the distinction between these views matters less than the shared conclusion. Gravity acts across enormous distances. It does not stop at the visible edge of a star or a galaxy. Its influence extends far beyond what telescopes can see. This is why galaxies begin interacting long before they appear to touch. As two galaxies approach each other, their gravitational fields overlap. Stars feel a gentle tug. Gas clouds shift slightly. Entire orbital patterns adjust over time. These effects accumulate slowly, reshaping both systems without any need for physical contact. It helps to imagine gravity as a conversation carried out across space. Nothing needs to collide for the message to be received. Mass alone is enough. This reach is especially important because most of a galaxy's mass is not concentrated in its bright center. Instead, it is spread throughout a vast halo dominated by dark matter. These halos extend far beyond the visible stars and gas, overlapping early during an encounter. Long before spiral arms cross, the deeper gravitational structures are already intertwined. As galaxies draw closer, gravity begins to stretch them. This stretching produces what astronomers call tidal forces. Tides occur whenever gravity pulls more strongly on one part of an object than another. On Earth, tidal forces from the Moon and the Sun gently raise and lower the oceans. In galaxies, the same principle operates on a much grander scale. When a galaxy enters the gravitational field of another, stars on the nearer side feel a slightly stronger pull than stars on the far side. Over millions of years, this difference elongates the galaxy. Spiral arms can be drawn outward. Long streams of stars can be flung into space, forming luminous arcs that trace the galaxy's past motion. These tidal features are not signs of impact. They are signatures of gravity working patiently over time. The timescales involved are essential to understanding why this process feels calm rather than violent. Galactic interactions unfold over hundreds of millions or billions of years. Each individual star responds slowly, adjusting its orbit bit by bit. There is no single moment when everything changes at once. Instead, the galaxy flows into a new shape, guided by gravity's persistent influence. There is a subtle beauty in this slowness. At human scale, change often comes through force and contact. At galactic scale, change comes through gradual rearrangement. Gravity reshapes without striking. It sculpts rather than shatters. This is also why galaxies can survive repeated encounters. A galaxy may experience multiple close passes with others over its lifetime, each one leaving a mark without destroying the whole. The structure evolves, but the system remains coherent. Observations from major astronomical institutions support this picture. Telescopes operated by space agencies and research observatories have captured countless interacting galaxies, revealing the same gravitational fingerprints again and again. Long tidal tails, distorted disks, and warped shapes all point to gravity acting across distance, not matter colliding at speed. Even the most dramatic-looking mergers tell this story. What appears chaotic in images is often the result of simple gravitational rules applied patiently over vast spans of time. The complexity arises not from violence, but from many small influences accumulating. This perspective reframes what it means for galaxies to collide. The word collision suggests impact, resistance, and sudden force. In reality, galactic collisions are better understood as episodes of gravitational negotiation. Each system adjusts to the presence of another, exchanging energy and momentum through the invisible geometry of space. The humour, if there is any, lies in how misleading appearances can be. Two galaxies may look like they're crashing into one another, yet their stars are gliding through an expanding web of gravitational influence, barely aware of their neighbours except through the slow bending of their paths. Once gravity is recognised as the true agent, the earlier ideas about emptiness fall into place. Space can be vast and matter sparse, yet interaction remains inevitable. Gravity bridges the gaps that matter leaves behind. This is the quiet engine behind every galactic encounter. No contact is required, no explosions are necessary. Gravity alone is sufficient to bring enormous systems together, reshape them, and guide them toward new forms over time. Understanding this allows the idea of a collision without touching to feel not just possible, but natural. In a universe built on gravity and scale, influence does not need impact. It only needs time. There is a hidden architecture to every galaxy, one that does not glow, does not cast shadows, and does not announce itself directly. Yet without it, galaxies would fly apart, mergers would not unfold as they do, and the universe would look nothing like it does. This invisible framework is known as dark matter. Dark matter earned its name not because it is sinister or mysterious by intention, but because it does not interact with light. It neither shines nor absorbs nor reflects. Telescopes cannot see it directly. Its presence is inferred through motion, through the way visible matter behaves as if something unseen is guiding it. If stars were the only source of gravity in a galaxy, their motion would follow a simple pattern. Stars near the centre would orbit quickly, held tightly by concentrated mass, while stars farther out would move more slowly, much like the planets in the solar system. But when astronomers measured how stars actually move, they found something unexpected. Stars far from galactic centres were orbiting just as fast as those closer in. According to visible matter alone, they should have been flung into space. This discrepancy was not subtle. It was consistent, persistent, and widespread across many galaxies. One of the scientists who played a crucial role in understanding this was Vera Rubin. By carefully studying galaxy rotation curves, which describe how orbital speed changes with distance from the centre, she helped demonstrate that galaxies contain far more mass than can be accounted for by stars and gas alone. Her work showed that something unseen must be present, extending well beyond the visible edges of galaxies. That unseen mass is now understood to form a vast halo around each galaxy. This halo is not a thin shell or a neat boundary. It is a deep, diffuse structure that can extend several times farther than the luminous stars and gas. Within this halo, visible matter moves, responds, and settles. In terms of mass, dark matter dominates. For a typical large galaxy, the majority of its gravitational influence comes not from the stars that define its shape, but from this invisible component. The stars are passengers riding within a much larger gravitational vessel. This has profound consequences for galactic collisions. When two galaxies approach one another, it is their dark matter halos that meet first. Long before spiral arms overlap or cores draw near, these halos begin to interpenetrate. Their gravitational fields merge, creating a combined environment that reshapes the motion of everything inside. From the perspective of visible matter, this invisible interaction sets the stage. Stars respond to changes in the gravitational landscape. Gas flows along new paths. Entire galactic disks can tilt, stretch, or warp as the underlying structure shifts. The collision, in other words, begins when nothing can be seen. This is one reason why galaxies can appear to influence each other at surprising distances. Long before any visible contact, subtle distortions appear. Streams of stars may be drawn outward. Rotation patterns change. These early signs reflect the meeting of dark matter halos rather than the interaction of luminous matter. The idea that most of a galaxy is invisible can feel unsettling at first. It challenges the instinct to trust what is seen. Yet the evidence is strong, supported by decades of observation and analysis from astronomical institutions around the world. Computer simulations make this even clearer. When researchers model galaxy mergers using only stars and gas, the results do not resemble real galaxies. The structures fall apart too easily. The shapes do not match observations. The timing feels wrong. Something essential is missing. When dark matter halos are included, everything changes. With dark matter present, simulated galaxies behave like real ones. They form realistic spiral arms. They develop tidal tails that match those seen in telescopes. They merge on timescales consistent with observation. The invisible mass provides the gravitational glue and guiding structure needed for the system to evolve correctly. These simulations rely on well-tested physical laws, applying gravity across millions of particles representing both visible and invisible matter. The fact that they reproduce observed galactic behavior so successfully is one of the strongest arguments for the role of dark matter in cosmic structure. There is a quiet elegance in this arrangement. The most important component of a galaxy is the one that does not announce itself. Light draws attention, but gravity does the work. During a merger, the overlapping dark matter halos deepen the combined gravitational well. This affects how quickly the galaxies lose energy and spiral toward one another. It influences whether the final result is a smooth elliptical galaxy or a distorted remnant still forming stars. It even affects how central black holes eventually find one another. All of this happens without contact, guided by mass that cannot be seen. The humour, if one can call it that, lies in how backwards this feels. The brightest parts of a galaxy are not its backbone. The glowing stars are decorative compared to the dark scaffolding that holds everything together. The collision of galaxies is therefore shaped primarily by something invisible, something known only by its effects. This does not mean dark matter is mysterious in every sense. Its gravitational behavior is well understood. What remains unknown is its exact nature, what it is made of at the particle level. Yet for understanding galactic collisions, its role is clear. It provides the extended reach of gravity that allows galaxies to sense one another long before they meet. In this way, dark matter extends the ideas already introduced about gravity acting across emptiness. It explains how that gravitational influence is structured and sustained. It turns gravity from a simple force into a vast layered field that shapes motion on the larger scales. When galaxies collide without touching, it is their dark matter halos that truly collide. The visible stars and gas follow along, tracing patterns written by an unseen hand. The encounter unfolds not as a clash of objects, but as a slow reconfiguration of invisible mass-guiding luminous matter into new arrangements. Understanding this hidden structure completes an important part of the picture. Emptiness allows galaxies to pass through one another. Gravity allows them to interact. Dark matter determines how that interaction unfolds. Together, these elements explain why galactic collisions look dramatic yet remain calm, why change is profound yet gradual, and why the most influential part of the process remains forever out of sight. Up to this point, stars have dominated the picture, and for good reason. They are the most visible parts of a galaxy, the points of light that define its shape and draw the eye. Yet when galaxies pass through one another, stars behave almost politely. They keep their distance. They adjust their paths gently. They rarely, if ever, collide. There is, however, one component of a galaxy that does not have the luxury of such wide personal space. That component is gas. Unlike stars, gas is not compact. It does not occupy neat, well-defined orbits as individual objects. Galactic gas exists as sprawling clouds, filaments, and diffuse regions that can stretch across hundreds or thousands of light years. It fills much more of the space between stars, even though it contributes far less mass overall. And because of this spread-out nature, gas behaves very differently when galaxies interact. When two galaxies approach each other, their stars pass through overlapping space with ease. Gas clouds do not. They encounter other gas clouds, and when they do, something finally makes contact. Gas cannot simply pass through gas without consequence. As clouds from one galaxy meet clouds from another, they begin to compress. Motion slows, energy builds, the gas heats up. Instead of gliding past, the material bunches together, thickening and changing state. This is where the calm, near-invisible interaction of stars gives way to something more active. The process is not explosive in the cinematic sense, but it is transformative. As gas compresses, it forms regions of higher density. Pressure rises, heat increases. In some places, the gas becomes hot enough to glow, emitting light that telescopes can detect. In others, the compression sets the stage for collapse, where gravity finally gains the upper hand and begins pulling material inward. These compressed regions are the seeds of new stars. Galactic mergers are therefore often associated with bursts of star formation, known as starburst regions. These are areas where stars are born at rates far higher than usual, sometimes dozens or hundreds of times faster than in calmer galaxies. The collision does not destroy stars, it creates new ones. This is one of the great ironies of galactic interaction. The same event that distorts and reshapes galaxies also lights them up with fresh stellar activity. Observations from major space-based and ground-based observatories have made this clear. Images captured by the Hubble Space Telescope reveal bright knots of star formation in interacting galaxies, especially along distorted arms and tidal features. These regions glow blue, indicating young, hot stars that formed recently from compressed gas. At longer wavelengths, observatories such as ALMA, the Atacama Large Millimeter Array, peer through dust and trace cold molecular gas directly. These observations show dense gas reservoirs piling up in merging systems, exactly where theory predicts they should. Where gas concentrates, stars soon follow. This behavior highlights a crucial contrast between stars and gas. Stars are effectively collision-proof because they are small and widely spaced. Gas clouds, by contrast, are large and diffuse. They overlap easily. When they do, their particles interact, exchanging energy and momentum. The result is friction, heating, and compression, processes that simply do not occur for stars passing through one another. This makes gas the true site of interaction during a galactic merger. The idea of shock fronts helps clarify what is happening, even without technical language. When two streams of gas meet at high relative speed, neither can continue unimpeded. Instead, a boundary forms where motion slows abruptly. Energy that once existed as movement is converted into heat. The gas becomes hotter, denser, and more turbulent. These shock regions ripple through the merging galaxies, reshaping their internal structure. Gas that once drifted quietly can be driven inward toward galactic centers, feeding star formation or even central black holes. Other gases flung outward into extended streams, enriching intergalactic space. The entire process unfolds slowly by human standards, but it is decisive by galactic ones. Importantly, gas makes up only a small fraction of a galaxy's total mass, yet its influence during mergers is outsized. Gas determines where new stars form. It controls how brightly a merging galaxy shines. It influences how quickly the system settles into a new shape. In this sense, gas acts as the mediator between gravity and light. Gravity sets the stage, dark matter provides the structure, stars trace the motion, but gas responds actively, transforming energy into visible change. There is also an element of feedback involved. Newly formed stars do not remain quiet. They emit radiation. They produce stellar winds. Some eventually explode as supernovae. These processes inject energy back into the surrounding gas, heating it and sometimes pushing it outward again. Star formation can therefore regulate itself, turning on and off in waves. This feedback helps explain why starbursts are intense but temporary. A merger can trigger a surge of star formation, but it does not continue indefinitely. Gas is consumed, heated, or dispersed, and the system gradually settles. Throughout all of this, the contrast with stellar behavior remains striking. While gas collides, compresses, and transforms, stars remain largely unaffected by direct contact. They follow new orbits shaped by gravity, but they do not feel the heat or pressure of the gas around them. From the inside of a galaxy, the consequences would be subtle. Over millions of years, the sky might brighten slightly as new stars form. Nebulae might become more common, yet nothing would feel like a collision. The drama unfolds on scales and timescales far removed from individual experience. There is a gentle humour in this arrangement. The component that looks insubstantial, thin, and ghost-like in images is the one that actually interacts. The bright, solid-looking stars are the ones that pass through untouched. By identifying gas as the place where interaction truly happens, the picture of galactic mergers becomes more complete. The calm passage of stars explains why destruction is rare. The active response of gas explains why change still occurs. Galaxies do not collide by smashing their stars together. They collide by compressing their gas, lighting up their interiors, and quietly reshaping themselves from the inside out. In a universe defined by emptiness, it is this thin, drifting material that finally makes contact and leaves the most visible mark. Understanding the role of gas resolves another apparent contradiction. How can galaxies pass through one another without touching, yet emerge transformed? The answer lies in recognizing that not all components behave the same way. Some glide, some collide. And it is the colliding component, light and diffuse though it may be, that writes the most dramatic chapters of galactic change. One of the quiet reasons galactic collisions feel so calm is that they unfold on timescales the human mind was never built to grasp. On Earth, events are measured in seconds, minutes, and years. Even the longest processes most people encounter fit comfortably within a single lifetime. Mountains rise and erode over millions of years, but those changes are inferred rather than experienced. Weather shifts in hours. Civilizations rise and fall over centuries. History feels long when it stretches back a few thousand years. Galactic mergers operate on a completely different clock. When two galaxies begin to interact, the process typically spans hundreds of millions to billions of years. The first gravitational influence may begin long before the galaxies appear close together. Subtle distortions build slowly. Orbits adjust. Gas begins to drift. Long before there is anything recognizable as an overlap, the merger has already begun. From start to finish, a full merger can take longer than many stars live. Massive, bright stars burn through their fuel quickly, shining for only a few million years before ending their lives. Smaller stars like the Sun persist for billions of years. Some of the smallest stars will outlive the current age of the universe. Against this backdrop, a galactic merger is neither fleeting nor eternal. It unfolds slowly enough to feel static, yet quickly enough to reshape entire systems. To put this into perspective, consider human history. Modern humans have existed for a few 100,000 years. Recorded history spans only a small fraction of that time. The rise and fall of empires, the development of science, the entire written record of civilization occupies less than a blink on a galactic timescale. If a galactic merger were compressed into a single year, all of recorded human history would occupy less than a single second. This mismatch in scale explains why mergers appear frozen in photographs. When telescopes capture images of interacting galaxies, the structures look dramatic but static. Spiral arms stretch outward. Tidal tails arc into space. Two bright cores hang suspended in apparent tension. Nothing seems to move. That is not because nothing is happening, but because everything is happening too slowly to notice. A single exposure from a telescope might last minutes or hours. Even observations taken years apart show almost no visible change. Compared to the billions of years over which mergers unfold, a human lifetime is effectively zero. This stillness can be misleading. The shapes seen in images are not permanent. They are momentary states in an extremely long process. The fact that they appear fixed says more about the observer than about the event itself. Astronomers understand this by combining observation with modelling. By studying many galaxies caught at different stages of interaction, and by simulating their motion over time, they can reconstruct the full sequence. What appears as a frozen sculpture is actually a slow-motion film stretched far beyond human perception. This slowness is essential to why galactic collisions are gentle rather than catastrophic. When change happens gradually, systems can respond smoothly. Stars adjust their orbits little by little. Gas flows redistribute over millions of years. Energy is absorbed, radiated, and dissipated without overwhelming any single component. There is no sudden shock that tears the system apart. In contrast, rapid changes tend to be destructive. On Earth, sudden impacts cause damage precisely because they happen faster than materials can respond. In galaxies, nothing happens quickly. Gravity applies its influence patiently, allowing structures to bend rather than break. This also explains why galaxies can undergo multiple interactions over their lifetimes. A galaxy may pass near another, be distorted, then drift away again, carrying the memory of that encounter in its shape. Later, it may meet another neighbor and be reshaped again. Each interaction layers change upon change without erasing what came before all at once. There is calm logic to this pacing. The universe has no need to hurry. With billions of years available, processes can unfold at speeds that preserve stability while still allowing transformation. This is why even dramatic-looking mergers are survivable. The system has time to adapt. For individual stars within a galaxy, the merger may feel almost irrelevant. Over the course of a star's orbit, the overall gravitational environment changes only slightly. A star completes millions of revolutions while the galaxy slowly shifts around it. From the star's perspective, the universe remains largely the same, even as the galaxy evolves on a grand scale. This perspective also helps explain why mergers do not feel violent from the inside. There is no single moment of impact, no sudden catastrophe to mark the event. Instead, the night sky would change so slowly that no generation of observers would notice the full transformation. Patterns would shift imperceptibly. New stars would appear. Old structures would fade. There is something quietly amusing about the mismatch between scale and perception. The largest collisions in the universe unfold at speeds so slow they resemble stillness. The most dramatic events appear calm precisely because they take their time. Scientific institutions that study galaxy evolution often speak in terms of billions of years because there is no smaller unit that makes sense. When describing mergers, phrases like gradual, extended, and long-lived are not rhetorical choices. They are necessities imposed by scale. Once this sense of time settles in, the entire idea of galactic collision changes character. What might sound like a crash becomes more like a slow blending. What might be imagined as destruction reveals itself as patient rearrangement. This reframing is crucial. Without it, the behavior of galaxies seems puzzling or counterintuitive. With it, their calm resilience becomes inevitable. Space is vast. Gravity is gentle. Time is abundant. Understanding these timescales allows the listener to slow down as well, to let go of expectations shaped by human speed and human experience. To view the universe not as a place of constant violence, but as a system where even the largest changes unfold with extraordinary patience. Galaxies collide without touching, not only because space is empty, but because time itself is generous. Long before galaxies appear to touch, long before their bright shapes overlap in images, something subtle begins to happen. Two vast systems, each moving through space on its own path, start to feel one another's presence. Nothing visible marks this moment. No boundary is crossed. No edge is breached. Yet from this point on, neither galaxy is entirely alone. Galaxies are never truly still. They orbit within groups and clusters, drifting along paths shaped by the gravity of their neighbors and the larger structure of the universe. These motions are slow and graceful, but they carry momentum. Each galaxy has direction, speed, and mass, and together these determine how encounters unfold. As two galaxies draw nearer, gravity begins to alter their trajectories. Their paths curve inward, not abruptly, but gently, like two dancers adjusting their steps as they circle a shared center. This is the beginning of a merger, though nothing yet looks dramatic. At this stage, the galaxies are still well separated. Their stars remain far apart. Their gas clouds drift quietly, but their gravitational fields are already overlapping, and that overlap changes everything. Each galaxy tugs on the other, pulling slightly more strongly on the near side than on the far side. This uneven pull is small at first, but over millions of years it accumulates. Stars begin to drift from their original paths. Gas responds more readily, flowing along newly shaped gravitational contours. The galaxies start to stretch. This stretching marks the first visible sign of interaction. Orbital dynamics play a central role here, though the idea itself can be understood without technical language. When two galaxies approach, they do not fall straight toward each other like dropped stones. Instead, they carry sideways motion, inherited from their long journeys through space. This sideways motion causes them to swing past one another, curving into elongated orbits rather than colliding head-on. As they do, something important happens. Energy and momentum are exchanged. Momentum is what keeps a moving object moving in a particular direction. In galactic encounters, momentum is not lost, but it is redistributed. The galaxies pull on each other, changing speed and direction slightly. Some material gains energy and is flung outward. Other material loses energy and sinks deeper into the combined gravitational field. This exchange does not happen all at once. It unfolds gradually as countless stars and gas clouds respond to the changing gravitational environment. The galaxies begin to slow relative to one another, setting the stage for closer encounters in the future. One of the most striking outcomes of this early interaction is the formation of tidal bridges and tails. A tidal bridge is a stream of stars and gas drawn out between two galaxies, connecting them like a luminous thread. It forms as gravity pulls material from one system toward the other, creating a shared structure that spans the space between them. These bridges can stretch for tens or even hundreds of thousands of light years, glowing faintly against the dark. Tidal tails, by contrast, sweep outward. As material gains energy during the encounter, it can be flung far from its original home, tracing long arcs that curve through space. These tails are among the most beautiful features seen in interacting galaxies, delicate and elongated, shaped by gravity rather than forceful ejection. Despite their dramatic appearance, these structures form quietly. Stars within them are not thrown violently, they're gently redirected, their orbits stretched into new paths that take them far from where they began. Astronomers have observed these features in many real systems. Telescopes operated by space agencies and research observatories have captured pairs of galaxies linked by faint bridges of light and surrounded by sweeping tails. These observations match what simulations predict, when gravity is allowed to act patiently over long timescales. What is remarkable is how early these features appear. Long before the main bodies of galaxies overlap, their outer regions can already be deeply affected. The visible interaction begins not at the centre, but at the edges, where gravity's differential pull is most effective. This early phase of a merger still feels calm. From within a galaxy, the changes would be subtle. Stars would follow slightly altered paths. Gas would drift inward or outward a little more readily than before. There would be no sudden disruption, no sense of impact. Yet from a cosmic perspective, the commitment has been made. Once galaxies enter this gravitational dance, escape becomes difficult. Each close pass robs them of a little orbital energy, binding them more tightly together. What begins as a near miss becomes, over time, a drawn-out embrace. There's gentle irony in calling this stage first contact. Nothing touches, no surfaces meet. The interaction is entirely mediated by gravity reaching across space. Contact in this context means influence rather than impact. This redefinition is essential. Without it, the early stages of a merger seem uneventful or incomplete. With it, they reveal themselves as the foundation on which everything else is built. The formation of bridges and tails is not decorative. These structures carry information about the galaxy's masses, their trajectories, and their past motion. Astronomers can study their shapes to infer how the encounter unfolded, much like reading the wake behind a moving boat. Even at this stage, the invisible components play a major role. Dark matter halos overlap and guide the redistribution of visible material. Gas responds more readily than stars, beginning to flow along the changing gravitational landscape. Stars, though slower to react, still feel the pull, their orbits subtly reshaped. All of this happens before any dramatic overlap of luminous disks. The galaxies remain recognizable as separate systems, yet they are no longer independent. There is something quietly elegant about this beginning. No fireworks announce it. No clear boundary marks the transition. Interaction emerges gradually, written into the motion of countless stars responding to a shared gravitational field. Understanding this phase helps explain why galactic mergers feel inevitable rather than violent. They do not begin with a crash. They begin with a conversation carried out through gravity, unfolding slowly as two massive systems start to acknowledge each other's presence. By the time the galaxies appear close together in images, much of the work has already been done. Orbits have shifted, material has been redistributed. The path forward has been shaped by choices made over millions of years. First contact, then, is less a moment than a process. It is the point at which separation gives way to interaction, not through touch, but through gravity's long reach. From here on, the galaxies move together, their futures increasingly intertwined, guided by forces that operate patiently across the vast emptiness of space. This is the moment that gives the title its weight, the point where two galaxies appear, unmistakably to occupy the same space. From a distance, this phase looks dramatic. Bright disks overlap, spiral arms interlace. Two glowing systems seem to merge into one tangled shape. To an eye trained on everyday experience, it looks like a collision in the most familiar sense. Surely something must be breaking. Surely stars must be crashing into stars. And yet, almost nothing of the sort is happening. As galaxies pass through one another, their stars continue along their paths largely unharmed. Each star moves according to gravity, tracing an orbit shaped by the combined mass of both galaxies. But even now, even at maximum overlap, the distances between individual stars remain enormous. The visual overlap is misleading. What appears crowded is still mostly empty. To appreciate this, it helps to return to scale. A typical star occupies a region a few million kilometers across. The space between stars, even in overlapping galaxies, is measured in trillions of kilometers. During a merger, the number of stars sharing the same region of space increases, but not nearly enough to eliminate the vast gaps between them. It is not that stars narrowly miss one another. It is that they are never close to begin with. Astronomers can estimate the likelihood of stellar collisions during this phase, and the numbers remain astonishingly small. Even in a full galactic overlap, the chance of any one star directly striking another is so low that it can be ignored for most practical purposes. A galaxy could pass cleanly through another and emerge with nearly all of its stars intact. This is the core resolution of the paradox. Galaxies collide without touching because their stars do not define their volume. Light fills the image, but space fills the structure. The same principle applies to planetary systems. A planetary system is an even smaller target than a star. Planets orbit within regions that are tiny compared to interstellar distances. When stars pass by other stars during a merger, those encounters are typically far too distant to disrupt planetary orbits. The gravitational influence weakens rapidly with distance. and most stellar flybys during a merger occur far outside the region where planets reside. From the perspective of a planet orbiting its star, the passage through another galaxy would likely go unnoticed. The night sky would change gradually. New stars might appear. Familiar patterns would distort over millions of years. But the local gravitational environment would remain stable. There is something quietly comforting in this idea. Even amid the largest rearrangements of cosmic structure, small systems can remain undisturbed. This stability helps dispel one of the most common misconceptions about galactic collisions. Popular descriptions often imagine stars smashing together, planets being flung into space, or entire systems being torn apart. These images are compelling, but they are wrong. The real danger to stars during a merger does not come from impact. It comes from gradual changes in gravitational potential. Orbits can become more elongated. Stars can be redistributed into new regions of the merged galaxy. Some may end up farther from the center than before, others may drift inward. But these are slow adjustments, not violent expulsions. The difference matters. Destruction implies sudden force. What galaxies experience is long-term reorganization. The stars survive. The system evolves. This is why astronomers studying merging galaxies focus less on collisions and more on dynamics. They track how stellar orbits change, how angular momentum is redistributed, and how energy is exchanged through gravity. The physics involved is subtle, cumulative, and patient. Even when galaxies pass directly through one another, the stars behave like two interpenetrating swarms. They share space without interacting directly, responding instead to the overall gravitational field. Once the overlap phase ends, the stars continue onward, carrying with them the memory of that shared passage in the form of altered orbits. There's also a visual trick at work. When two galaxies overlap, their light adds together. Bright regions stack atop one another, making the system appear denser than it truly is. This can give the impression of crowding where none exists. The eye is fooled by brightness, mistaking luminosity for solidity. In reality, the stars remain isolated points of fusion scattered across immense volumes. This overlapping phase does have consequences, but they are indirect. Gas clouds collide, compress, and heat, as already described. New stars form. Central regions may become more active, but the stars themselves continue almost unscathed. Even the cores of galaxies, where star densities are higher, rarely see direct collisions. These regions are dense by cosmic standards, but still sparse by human ones. The same principles apply, just on slightly smaller scales. From inside a galaxy, the experience would be anticlimactic. There would be no sudden shockwave, no dramatic flash. Over many millions of years, the sky would slowly transform. Constellations would stretch and twist. New bands of light might appear as gas ignites into star formation, but nothing would announce a moment of impact. The universe does not provide a clear marker for when one galaxy passes through another. There is no before and after in the way human events are defined. The process blurs together, stretched across time. This is perhaps the most counterintuitive lesson of all. The most visually striking phase of a galactic merger is also the least destructive. The moment that looks like a crash is the moment when the fundamental properties of space and scale assert themselves most strongly. Galaxies pass through one another because they can. Space allows it. Gravity guides it. Time stretches it out until violence becomes unnecessary. Astronomical observations reinforce this calm reality. Systems observed mid-overlap often show ordered stellar motion despite their tangled appearance. Simulations that track individual stars confirm that their paths remain smooth and continuous. The physics does not allow for widespread chaos because the conditions for chaos simply are not present. There is a quiet elegance in this resolution. The title promises a paradox, but the universe resolves it without drama. Collisions without touching are not exceptions or oddities. They are the natural outcome of structure, scale, and distance. By the time galaxies visually overlap, the story has already been written by emptiness and gravity. What unfolds is not destruction, but passage. Two vast systems share space, exchange influence, and continue on paths shaped by forces that operate far beyond the reach of intuition. Understanding this phase brings everything together. The emptiness between stars, the reach of gravity, the patience of time, and the subtlety of interaction all converge here. The paradox dissolves, replaced by a picture that is calmer, stranger, and far more satisfying than the idea of a cosmic crash. Galaxies collide without touching, not because something prevents impact, but because, at this scale, impact is simply not how the universe works. When galaxies pass through one another, the absence of destruction does not mean the absence of change. What follows the overlap is a long period of reshaping, where gravity continues its work not by breaking structures apart, but by gently pulling them into new forms. The result is distortion rather than devastation, transformation rather than collapse. At first glance, the shapes of interacting galaxies can look chaotic. Spiral arms appear stretched and twisted. Disks bend out of alignment. Bright cores drift away from their original centers. Yet beneath this apparent disorder lies a consistent pattern, shaped by tidal forces acting patiently over time. Tidal stretching is the same process that began when the galaxies first approached, but now it operates across the full extent of both systems. As gravity pulls unevenly on different regions, material responds according to how tightly it is bound. Loosely held stars and gas in the outer regions are the first to be drawn out, forming elongated arms and sweeping arcs that extend far into space. These features are not signs of damage, they're signatures of motion. Spiral arms, once neatly wrapped around galactic centers, can be pulled into longer, thinner structures. In some cases, they stretch so far that they detach visually, becoming tidal tails that trace the galaxy's path through space. These tails can contain billions of stars and vast amounts of gas, yet they remain gravitationally connected to the system, slowly evolving rather than dispersing. Galactic disks also respond to these forces. Rather than shattering, they warp. The flat plane of stars and gas bends upward or downward, forming subtle curves that ripple across the structure. From certain angles, these warps are barely noticeable. From others, they become striking, revealing the three-dimensional nature of the interaction. Even the central regions of galaxies can shift. The dense core, often containing a supermassive black hole, may become displaced from the geometric center of the visible structure. This does not mean the core has been knocked loose. Instead, it reflects changes in the overall mass distribution as stars and gas are redistributed by gravity. These distortions develop slowly. A warped disk does not snap into place. An elongated arm does not form overnight. Each change emerges from countless small adjustments, as individual stars alter their orbits slightly in response to a changing gravitational field. Over millions of years, these small changes add up to large-scale reshaping. What is remarkable is how resilient galaxies are throughout this process. Despite their altered appearance, interacting galaxies remain coherent systems. Stars continue to orbit. Gas continues to flow. even dramatic distortions rarely result in material being permanently lost. Much of what is drawn outward eventually falls back in, contributing to the final shape of the merged galaxy. This resilience is evident in both observation and simulation. Researchers working with space agencies such as NASA and ESA have used detailed computer models to follow galactic mergers from start to finish. These simulations track millions of particles representing stars, gas, and dark matter, allowing gravity to act naturally across vast spans of time. Again and again, the results show the same pattern. Galaxies stretch, twist, and deform, but they do not disintegrate. The simulations match what telescopes observe. Systems captured at different stages of interaction display the predicted features, from gently warped disks to spectacular tidal tails. The agreement between model and observation reinforces the idea that distortion is the expected outcome, not destruction. There is an important reason why galaxies respond this way. They are not rigid objects. They are collections of orbiting material held together by gravity. When that gravitational environment changes, the material adjusts smoothly rather than fracturing. Flexibility is built into the structure. This flexibility stands in sharp contrast to cinematic portrayals of cosmic collisions. Popular images often show galaxies exploding into clouds of debris or collapsing into chaos. In reality, there is no mechanism for such sudden ruin. The energies involved are spread across enormous volumes and timescales, allowing systems to adapt. The humour, if it can be called that, lies in how misleading the visuals can be. A galaxy with twisted arms and stretched tails looks wounded, yet it is functioning exactly as physics predicts. What appears broken is simply in transition. These distorted shapes are temporary, though they can persist for hundreds of millions of years. Over time, gravity continues to smooth out irregularities. Orbits become more random, distinct features blur together. Eventually, the system settles into a new equilibrium, often quite different from its original form. In many cases, repeated stretching and reshaping erases the orderly structure of spiral galaxies, leading to smoother, rounder systems. The elongated arms fall back inward. Warps relax. The final result may be an elliptical galaxy, supported not by rotation, but by the collective motion of stars in many directions. Even then, the history of interaction remains written into the system. Subtle variations in star motion, faint shells of stars far from the center, and lingering streams of material all tell the story of past encounters. The galaxy carries its distortions as memories rather than scars. From the inside, this entire process would feel uneventful. Stars would continue their long orbits. The changes would be too slow to notice within any single lifetime. There would be no sense of collapse or catastrophe, only a gradual rearrangement of the sky. Understanding this phase is essential to replacing the idea of cosmic violence with one of cosmic adaptation. Galaxies are not fragile. They are robust, flexible structures shaped by forces that act slowly and persistently. Distortion is how gravity expresses itself when given enough time. It stretches rather than breaks, reshapes rather than destroys. In galactic mergers, this gentle persistence is what allows enormous systems to change without falling apart. By focusing on transformation instead of destruction, the behavior of galaxies becomes easier to understand and far more interesting. The universe does not rely on sudden shocks to evolve. It relies on patience, scale, and the quiet power of gravity working over immense spans of time. In this light, the twisted shapes of interacting galaxies are not signs of chaos. They are evidence of a process unfolding exactly as it should, a reminder that even the largest changes in the universe are carried out with remarkable restraint. After galaxies pass through one another and their shapes begin to stretch and settle, something quietly remarkable often follows. In the wake of distortion and rearrangement, new light begins to appear. Not from explosions or destruction, but from creation. Galactic mergers have a reputation for triggering bursts of star formation, and this reputation is well earned. For a time, these systems can produce new stars at rates far higher than those seen in calmer, isolated galaxies. This increase is temporary, but while it lasts, it can transform the appearance and future of the merged system. The reason lies not in the stars themselves, but in the behavior of gas. As described earlier, gas is the component of a galaxy that truly interacts during a merger. When galaxies overlap, gas clouds compress, slow down, and heat up. Over time, much of this gas is driven into denser regions, especially toward the inner parts of the system. Gravity becomes more effective where gas piles up and conditions shift in a crucial way. Star formation begins with collapse. Under normal circumstances, large clouds of gas can drift for millions of years without forming stars. Internal motion, heat, and turbulence provide enough pressure to resist gravity's pull. A merger changes that balance. Compression increases density. Motion becomes chaotic. Shock waves ripple through clouds, dissipating energy that once supported them. As pressure support weakens, gravity gains the upper hand. Parts of the gas cloud begin to contract. The contraction is not smooth or uniform. Instead, it fragments. Dense knots form within the cloud, each one pulling in more material as it grows. Over time, these knots become hot enough at their centers to ignite nuclear fusion. A star is born. This process happens on scales far smaller than a galaxy, but it is the galactic merger that sets it in motion. By funneling gas into dense regions and stripping away stabilizing motion, the interaction creates ideal conditions for collapse. The result is a starburst. Starburst regions are areas where stars form rapidly and in large numbers. They can shine brightly in blue and ultraviolet light, dominated by young, massive stars that burn hot and fast. These regions often appear clumped along distorted arms, in compressed rings, or near galactic centers where gas has accumulated most strongly. Observations from major astronomical observatories have repeatedly shown this pattern. Merging galaxies often glow with clusters of young stars, their light piercing through surrounding dust. At wavelengths invisible to the human eye, these systems radiate intensely, revealing energetic processes tied directly to recent star formation. Yet this creative phase carries the seeds of its own ending. Young stars are not quiet residents of their birthplaces. Massive stars, in particular, release enormous amounts of energy. They emit intense radiation that heats nearby gas. They drive powerful stellar winds that push material outward. Some end their lives as supernovae, releasing sudden bursts of energy that can tear through surrounding clouds. These feedback processes act as a kind of regulation. As new stars form, they begin to disrupt the very gas that created them. Heating raises pressure. Winds carve out cavities. Shock waves stir turbulence back into the environment. Over time, this activity can halt further collapse, slowing or even shutting down star formation in that region. This is why starbursts do not last forever. Even in the most active mergers, the surge of star formation is temporary, typically lasting tens or hundreds of millions of years. Once the gas is consumed, heated, or dispersed, the system settles into a quieter state. Star formation continues at a lower rate, or in some cases becomes scarce altogether. There's a delicate balance at work here. Mergers concentrate gas and trigger collapse, but feedback ensures that the process does not run away indefinitely. Creation and suppression are tightly linked, each shaping the other. This interplay has lasting consequences for the merged galaxy. The burst of star formation enriches the system with heavy elements. Young stars fuse lighter elements into heavier ones, and when they die, those elements are returned to the surrounding gas. This chemical enrichment affects future generations of stars, planets, and potentially even life. In this sense, mergers act as engines of cosmic recycling. The distribution of stars also changes. Many of the newly formed stars end up in dense clusters, some of which may remain bound for billions of years. Others disperse into the broader galaxy, contributing to a smoother, more uniform stellar population. In some cases, repeated bursts of star formation during multiple encounters can exhaust much of a galaxy's cold gas. When this happens, the galaxy transitions into a quieter phase of its life, dominated by older stars and little new formation. This is one pathway by which galaxies evolve from active, star-forming systems into more passive ones. There is a subtle contrast worth noting. While mergers are often associated with intense activity, they do not create stars everywhere. The increase is localized, shaped by where gas flows and accumulates. Vast regions of the galaxy may remain relatively unchanged, continuing their slow evolution, while pockets of brilliance flare and fade. From the inside of such a system, the changes would still feel gentle. Over millions of years, the sky would brighten in certain regions as clusters of young stars appear. Nebulae would glow more intensely. Over even longer timescales, those bright stars would age and dim, blending into the background as new generations take their place elsewhere. The humour, if there is any, lies in how unassuming the trigger is. A merger does not smash stars together to create new ones. It simply nudges gas into the right conditions, and then lets gravity do what it does best. This creative aftermath reinforces an important theme. Galactic collisions are not purely destructive or transformative in a negative sense. They're part of a cycle. Interaction leads to compression. Compression leads to creation. Creation leads to feedback and balance. In this way, mergers contribute to the long-term evolution of galaxies across the universe. They help explain why star formation was more common in the distant past, when mergers were more frequent. They also help explain why many galaxies today are quieter, having already undergone these intense phases earlier in their histories. Understanding star formation in the aftermath of a merger completes another piece of the puzzle. The same processes that allow galaxies to pass through one another without touching also allow them to renew themselves. Emptiness and gravity make gentle interaction possible. Gas turns that interaction into light. Creation emerges not from collision in the everyday sense, but from compression, patience, and time. The aftermath of a merger is not a graveyard of broken stars. It is often a nursery, briefly luminous, quietly shaping the next chapter in a galaxy's long life. As galaxies reshape and settle after their long passage through one another, attention naturally drifts inward, toward the densest regions at their centers. Here, buried deep within the gravitational heart of each galaxy, lies an object that seems to promise drama, a supermassive black hole. These black holes are extreme by any standard. Each contains millions or billions of times the mass of the Sun, compressed into a region smaller than a planetary system. Their gravity governs the motion of stars and gas in the central core, and their activity can influence an entire galaxy. It is tempting, then, to imagine that when galaxies merge, their central black holes must rush together in a violent finale. The reality once again is quieter and far more patient. When two galaxies begin to merge, their central black holes do not immediately meet. At first, each black hole continues to sit near the center of its own stellar population, surrounded by stars and gas that move with it. As the galaxies distort and overlap, these cores drift closer together, but they do so slowly, carried along by the mass around them, rather than plunging directly inward. The journey of a black hole during a merger is shaped by its surroundings. As a galaxy moves through another, its stars and gas experience gravitational drag. This process, known informally as dynamical friction, acts like a gradual braking force. The black hole, embedded within its dense stellar core, loses orbital energy over time and spirals inward toward the center of the newly forming system. This does not happen quickly. It can take hundreds of millions or even billions of years. For long periods, the merged galaxy may contain not one, but two supermassive black holes orbiting each other at a respectful distance. They form what astronomers call a black hole pair or binary, though even here the word pair should not suggest closeness by human standards. The separation between them can be measured in light years, with vast numbers of stars passing between them undisturbed. During this phase, the black holes are not colliding, they are dancing. Their orbits gradually shrink as they interact with surrounding stars and gas. Each close pass transfers a tiny amount of energy outward, allowing the pair to move closer together. This process is slow and inefficient, especially once the black holes reach separations smaller than the surrounding stellar environment can easily influence. This leads to an important clarification. Black hole mergers are not an automatic or immediate outcome of galactic mergers. In fact, they are relatively rare events, and when they do occur, they are delayed far beyond the initial collision of the galaxies themselves. Some galaxy mergers may never produce a black hole merger at all. The black holes may remain in wide orbits, or one may be ejected slightly from the center through complex gravitational interactions. The idea of every galactic merger ending in a dramatic black hole collision is a misconception. When black holes do eventually draw very close together, another subtle process takes over. At extremely small separations, the orbiting black holes begin to lose energy not through interactions with stars or gas, but through gravitational waves. These are ripples in space and time itself, predicted by Einstein's general theory of relativity and confirmed through observation. Gravitational waves carry energy away from the system, allowing the black holes to spiral inward more rapidly. This final stage unfolds invisibly, without light, without heat, without impact. Space itself does the work. The detection of gravitational waves by observatories such as LIGO and Virgo has provided direct evidence that black hole mergers occur in the universe. These detections typically involve stellar mass black holes, much smaller than the supermassive ones at galactic centers, but the same physical principles apply. For supermassive black holes, the gravitational waves produced would be far lower in frequency, stretching across longer timescales. Detecting them directly remains a challenge, but astronomers are developing methods to search for their subtle signatures using precise measurements of distant objects. Even here, the tone remains calm. A black hole merger is not an explosion. It does not produce light or shock waves that tear galaxies apart. It is a quiet release of energy into the fabric of space and time, brief on cosmic scales, yet gentle compared to popular imagination. Throughout all of this, the surrounding galaxy remains largely unaffected. the merger of two supermassive black holes does not destabilize stars across the system. The influence is confined to the very central region, and even there, it manifests as slight changes in motion rather than destruction. Gas near the center can be affected, however, and this is where black holes make their presence known more visibly. As gas flows inward during a galactic merger, some of it can be captured by the central black holes. When this happens, the gas heats up as it spirals inward, releasing energy in the form of radiation. The galaxy's core can brighten dramatically, becoming what astronomers call an active galactic nucleus. These active phases can be powerful, launching jets and winds that push gas outward and regulate further star formation. Yet even this activity is episodic. It turns on and off as fuel becomes available or is exhausted. It does not represent a permanent or runaway state. There is an understated balance at work. Black holes respond to the merger by moving inward slowly. They influence their surroundings by shaping gas flow and energy release, but they do not dominate the process. They are participants, not protagonists. This perspective is important because black holes often attract outsized attention. Their name alone suggests catastrophe. In reality, they are governed by the same principles of gravity, scale, and time that shape everything else in the universe. From a broader view, the behavior of central black holes during mergers reinforces a recurring theme. Even the most extreme objects follow the same calm rules. Change happens gradually, outcomes are delayed, influence spreads quietly rather than violently. From within a galaxy, the presence of two central black holes would not announce itself dramatically. Stars would continue to orbit. The sky would remain stable. Only over immense spans of time would subtle shifts accumulate, guiding the system toward a new equilibrium. There is also a gentle irony here. The most massive, compact objects in the universe are among the slowest to complete their mergers. Their gravity is immense, yet the distances involved and the need to shed energy make their union a drawn-out affair. Understanding this helps place black holes back into context. They are extraordinary, but they do not override the broader behavior of galaxies. They fit into it. By narrowing focus from the full galactic scale to the central regions, the picture becomes clearer rather than more dramatic. The same principles apply everywhere. Emptiness prevents collisions, gravity enables interaction, time smooths change. Even at the core of a merging galaxy, where mass and energy are concentrated, the universe resists sudden endings. Supermassive black holes approach one another slowly, guided by their surroundings, releasing their energy not in fire or impact, but in faint ripples that pass silently through space. This calm conclusion to what might seem like the most extreme outcome completes another part of the story. Galactic mergers do not culminate in cosmic catastrophes. They culminate in quiet rearrangements, even at their very centers. The universe, it seems, prefers patience over spectacle, even when black holes are involved. After the long approach, the overlap, the stretching, and the bursts of new stars, the merger enters its quietest phase. The drama fades, not because nothing is happening, but because the system is finally settling. Two galaxies that once moved independently now behave as a single structure, bound together by a shared gravitational center. This settling process takes time. There is no clear moment when two galaxies officially become one. Instead, their identities blur gradually as stars, gas, and dark matter redistribute themselves into a new balance. Orbits that once traced distinct paths around separate centers now belong to a combined gravitational field. At this stage, the most obvious changes are no longer sudden or dramatic. They are smoothing processes. Stars that were once arranged in neat rotating disks begin to move in more varied directions. Some still follow roughly circular paths, but many are scattered into elongated or tilted orbits. Over hundreds of millions of years, these motions mix together, erasing the ordered patterns that once defined spiral structure. This mixing is known as dynamical relaxation. Dynamical relaxation is not a single event, but a long process through which a system redistributes energy and momentum among its components. As stars pass through regions of varying gravitational strength, their orbits change slightly. Each interaction is small, but over time the cumulative effect is significant. The result is a loss of memory. The galaxy gradually forgets how it was assembled. Spiral arms fade, clear disks dissolve. What remains is a smoother, rounder distribution of stars supported not by rotation in a single plane, but by the collective motion of stars in many directions. This is why many major mergers produce elliptical galaxies. Elliptical galaxies lack the obvious spiral arms and flat disks seen in spiral systems. Instead, they appear as smooth, rounded, or elongated shapes, with stars moving on a wide variety of orbits. The structure reflects the history of mixing and relaxation rather than orderly rotation. In a merger between galaxies of similar size, the disruption is often strong enough to destroy the original disks entirely. The rotational patterns that once held spiral arms in place are scrambled. Without a dominant disk of cold gas to reform the structure, the galaxy settles into an elliptical form. This outcome is not guaranteed. Mergers involving very unequal masses or systems rich in gas can produce different results. In some cases, a disk can reform after the merger, especially if fresh gas continues to flow into the system. But for many large mergers, the elliptical shape is the natural conclusion. The transition feels dramatic when viewed across billions of years, yet it remains calm on any shorter timescale. Stars are not flung violently into space. They are reassigned to new roles within the combined system. Some end up closer to the center, others occupy the extended outer regions. A few may form faint shells or streams that linger far from the core, subtle traces of the merger's past. Gas behaves differently during this settling phase. Much of it has already been consumed by star formation or heated by feedback processes. What remains may sink toward the center, contribute to residual star formation, or be expelled into the surrounding environment. The final galaxy often contains far less cold gas than its progenitors. This change has long-term consequences. With less gas available, star formation slows. The galaxy begins to age. Its light becomes dominated by older, redder stars. The bright blue glow of starburst regions fades, replaced by a steadier, softer illumination. From a distance, the galaxy now looks calm and mature. Its turbulent youth is written only in subtle details, visible to careful observation, but invisible to casual glance. This settling phase also marks the end of the merger as a distinct event. From here on, the galaxy evolves as a single system, responding to its environment, accreting small companions, or drifting quietly through space. The long interaction narrative resolves into stability. There is something quietly satisfying about this conclusion. Despite all the stretching, overlap and change, the galaxy does not collapse into chaos. It does not shatter. It finds a new equilibrium. Gravity, having driven the interaction, now smooths the result. The idea of loss is central here, but it is a specific kind of loss. What disappears is not matter, but structure. The original patterns that defined each galaxy give way to something simpler and more uniform. The system trades complexity of form for stability of motion. This trade is a common theme in physics. Systems tend towards states where energy is distributed more evenly. In galaxies, this means stars moving in many directions rather than marching in neat, ordered paths. There is gentle humour in how understated this ending is. After billions of years of interaction, the final result is not a spectacular finale, but a quiet settling. Two galaxies become one not through a climactic moment, but through patience. From the inside, the transition would be almost impossible to notice. No observer would see the moment when individuality was lost. The sky would change slowly. Over countless generations, familiar patterns would blur and fade. New constellations would emerge, not by design, but by drift. Scientific observations support this picture. Surveys of galaxies across the universe show a wide range of shapes and structures, reflecting different histories. Elliptical galaxies tend to be more common in dense environments where mergers are frequent. Spiral galaxies are more common in quieter regions where interactions are rare. The correlation tells the same story again and again. The universe remembers its pass-through structure. Yet even as structure fades, the galaxy remains alive. Stars continue to shine. Planets continue to orbit. The system persists, reshaped but intact. This structural conclusion brings closure to the merger process itself. The long sequence of approach, overlap, distortion, and creation resolves into a single, stable form. The collision without touching has run its course. What remains is a reminder of how the universe handles change, not with sudden endings, but with gradual blending, not with destruction, but with rearrangement. Two galaxies become one not because one conquers the other, but because gravity allows them to share space, exchange motion, and eventually settle into a common rhythm. The process is slow, subtle, and deeply consistent with the calm logic that governs everything on the larger scales. By the time the merger is complete, the drama is long past. What endures is a new galaxy, quietly carrying the combined history of its predecessors, moving forward through space as a single unified system. Among all the distant mergers scattered across the universe, there is one that feels unusually personal. It involves the galaxy that contains every star visible in the night sky, and a neighbouring system already familiar to astronomers for centuries. Far in the future, the Milky Way and the Andromeda Galaxy will begin a long, slow encounter of their own. This future merger is not speculation. It is a measured prediction, grounded in careful observation of motion across space. Astronomers have tracked Andromeda's position and velocity with increasing precision, and the conclusion is clear. The two galaxies are moving toward one another, drawn together by gravity, destined to interact. The timescale, however, is reassuringly vast. Current estimates place the first close approach several billion years in the future. The full merger will take even longer, unfolding across spans of time that far exceed human history. Nothing about this event is sudden. Nothing about it is urgent. The knowledge comes in large part from detailed measurements of stellar motion made by the Gaia mission. By mapping the positions and velocities of more than 1 billion stars within the Milky Way, Gaia has provided an extraordinarily precise picture of how our galaxy moves through space. Combined with measurements of Andromeda's motion, this data allows astronomers to reconstruct the future paths of both systems. What emerges is not a head-on crash, but a slow gravitational dance. Andromeda is currently more than 2 million light-years away. At that distance, the galaxies already influence one another, but only faintly. Over time, their mutual pull will alter their paths, curving them inward. The first encounter will stretch both galaxies, drawing out tidal features much like those seen in other mergers across the universe. From the outside, the process will look familiar. From the inside, it will feel remarkably calm. One of the most common reactions to hearing about this future collision is concern. Will stars collide? Will planetary systems be disrupted? Will life be threatened? The physics explored throughout this story provides a clear answer. The risk to individual stars is essentially negligible. Even when the Milky Way and Andromeda overlap, the vast distances between stars remain. The chance of any given star colliding with another star is extraordinarily small. The same is true for planetary systems. Planets orbit stars on scales that are tiny compared to interstellar separations. Most stellar flybys during the merger will occur far too distant to disturb planetary orbits. From the perspective of a star like the Sun, the merger would be a slow change in scenery rather than a violent event. Over millions of years the night sky would transform. Andromeda would grow larger, brighter, and more complex. New streams of stars would appear. Familiar patterns would stretch and fade. But the local environment would remain stable. There is something quietly comforting in this. The future merger reminds us that even events involving entire galaxies do not necessarily threaten the small scales that matter most to individual systems. The universe is structured in such a way that large-scale change does not require small-scale destruction. Gas dynamics will play a more active role, as in all mergers. As the galaxies interact, gas clouds will compress, triggering new waves of star formation. The Milky Way may experience periods of increased stellar birth, especially during close passes. These episodes will be bright and energetic on galactic scales, yet spread across enough time to remain gentle. Eventually, after multiple passes, the two galaxies will settle into a single system. The result is often referred to informally as a new galaxy, formed from the combined mass of both. Its structure will depend on how much gas remains and how energy and motion are redistributed during the interaction. Many simulations suggest that the final outcome will resemble a large elliptical galaxy, supported by stars moving in many directions rather than a thin rotating disk. The familiar spiral structure of the Milky Way is unlikely to survive intact. But again, this change unfolds slowly. There is no moment when the galaxy suddenly becomes something else. The future Milky Way will not notice the transition in the way a living being notices an event. It will simply continue evolving. It is also worth noting that the Sun itself won't be present to witness the merger. Long before the galaxies interact, the Sun will exhaust its nuclear fuel and change state. The story of the merger belongs to distant future generations of stars and planets, not to the present sky. This perspective helps keep the event grounded. The merger is real, but it is not a threat. It is part of the normal life cycle of galaxies in groups like our own. The local group, which contains the Milky Way, Andromeda, and dozens of smaller galaxies, is a gravitationally bound family. Over time, its members interact, merge, and rearrange. The future collision is simply the largest chapter in a much longer story that has already unfolded many times. There is also a quiet symmetry in applying everything learned so far to a familiar system. The emptiness between stars, the reach of gravity, the role of dark matter halos, the patience of time. All the principles explored in distant galaxies apply just as clearly here. Nothing special or exceptional happens because the galaxies involved are our own. The same rules govern all systems without favour or urgency. From an imaginative standpoint, the future merger offers a gentle exercise in perspective. One can picture the night sky slowly changing generation after generation, Andromeda's core growing more detailed, streams of stars arcing across the darkness, new constellations forming not by chance but by drift. There is even room for light humour in this cosmic inevitability. The Milky Way is not being invaded. It is participating in a long-scheduled interaction, following gravitational agreements set billions of years ago. No alarms are necessary. No countdown clocks apply. Astronomers studying this future event do so not out of concern but out of curiosity. It provides a nearby laboratory for understanding mergers in general. By knowing what will happen here, scientists can test their models against a real evolving system, even if the full process will never be observed directly. In that sense, the future collision is already valuable. It connects abstract theory to a concrete example. It anchors the vast ideas of galactic evolution to a place that feels close and familiar. By bringing the story home, the merger between the Milky Way and Andromeda reinforces the central message. Galactic collisions are not catastrophic impacts. They are long conversations carried out through gravity and time. When our galaxy eventually passes through another without touching, it will do so quietly, patiently, and without harm to the stars that call it home. The universe does not rush its changes, even when entire galaxies are involved. Understanding this allows the future to feel less threatening and more instructive. The Milky Way's fate is not one of destruction, but of transformation, unfolding slowly, predictably, and with remarkable calm. From the outside, galactic mergers look dramatic. From the inside, they are almost imperceptible. For any observer living within a galaxy undergoing a merger, there would be no moment that felt like an event. No sudden flash, no shock wave, no clear before and after. Instead, change would arrive so slowly that it would be indistinguishable from normal cosmic drift. The most noticeable difference would be in the night sky, and even that would unfold at a pace far slower than memory. Over millions of years, the familiar patterns of stars would begin to stretch. Constellations, if they existed, would subtly distort. Stars that once appeared close together would drift apart, while others would seem to draw nearer. These changes would not be dramatic from one generation to the next. They would require careful comparison across immense spans of time to detect it all. A neighbouring galaxy involved in the merger would gradually grow larger and more detailed. At first it might appear as a faint smudge, similar to how Andromeda looks from Earth today. Over many millions of years, that smudge would brighten and spread, revealing structure. Dark lanes of dust might become visible. Star-forming regions would glow softly. Eventually the sky would contain not one dominant band of stars, but overlapping streams and arcs. Yet even this visual transformation would feel gentle. The sky would not suddenly fill with light. There would be no overwhelming brightness. The added stars would still be separated by vast distances, their light arriving calmly across space. Night would remain night. Darkness would still dominate. For life on planets orbiting stars within the galaxy, the merger would pose little direct threat. The physics that protects stars from collision also protects planetary systems. The distances involved ensure stability. Most stars would never pass close enough to disturb planetary orbits in any meaningful way. A planet like Earth could continue circling its star, unaware that its galaxy was in the midst of a vast interaction. Days would pass, seasons would change, evolution would proceed. Civilizations could rise and fall without ever noticing that their home galaxy was sharing space with another. This continuity is one of the most counterintuitive aspects of galactic mergers. Large-scale change does not imply small-scale danger. The universe is structured so that immense systems can rearrange themselves, while leaving their smallest components intact. Gravity acts gently at local scales, even when it drives profound change across entire galaxies. There would be no increase in stellar radiation dangerous enough to threaten life simply because of the merger. While star formation may increase in certain regions, these regions would be far away, separated by thousands or millions of light years. The additional light would contribute to the overall glow of the sky, not to harmful exposure. Cosmic radiation levels would remain dominated by local stellar processes, not by the distant rearrangement of galaxies. Even supernovae triggered by increased star formation would be too far away to matter. Their light might be visible, their effect would not be felt. The experience of time would remain unchanged. A merger unfolds over hundreds of millions to billions of years. For any individual observer, or even for a long-lived species, the process would feel static. The sky of childhood would look much like the sky of old age. Only careful records, passed down across many generations, could reveal the slow transformation taking place. This slowness has an important psychological consequence. It removes urgency. There would be no reason to prepare, no reason to respond, no reason to adapt. The merger would not impose new constraints on daily life. It would simply form part of the background story of the universe, unfolding quietly while local concerns continue to dominate attention. From an imaginative standpoint, the changing sky would be subtle but beautiful. Streams of stars might gradually appear where none existed before. The bright band of the galaxy could thicken or split. New star clusters would ignite in the distance, adding faint points of light to the darkness. Over very long timescales, the sky might become richer, more complex, more layered. Yet it would never feel crowded. The same emptiness that defines galaxies would preserve a sense of space and depth. There is a temptation to imagine observers watching galaxies crash overhead like celestial storms. This image is compelling, but it misunderstands scale. Galaxies do not rush past one another, they seep through each other. Their motion is measured in kilometers per second, but spread across distances so vast that movement becomes almost abstract. Even the closest stellar flybys during a merger would likely occur at distances far greater than those between stars today. The gravitational influence of such flybys would be negligible for planets. Stability would remain the norm. This perspective helps humanize the process without placing humanity at the center. The merger does not happen for observers. It happens regardless of them. Observers simply exist within it, largely unaffected. Life, if it arises, would continue to evolve according to local conditions. Biology responds to climate, chemistry, and energy sources, not to the slow drift of galaxies. A merger does not alter a star's output in any significant way. It does not change planetary chemistry. It does not rewrite the rules of habitability. In this sense, galactic mergers are excellent reminders of scale. They demonstrate how disconnected different layers of the universe can be. What matters enormously at one scale can be irrelevant at another. From the perspective of an observer inside a galaxy, the most meaningful changes would still be local. The motion of a planet around its star, the evolution of a biosphere, the rise of intelligence. These processes unfold on timescales and distances that remain untouched by the merger. The galaxy provides a backdrop, not a driver. There is also a gentle humility in recognizing how little an observer would notice. The universe is not arranged to announce its largest events to those living inside them. Change does not always arrive with spectacle. Sometimes it arrives as a barely perceptible shift in the pattern of distant lights. If records were kept over millions of years, future astronomers within the galaxy might eventually recognize what was happening. They would measure stellar motions, map gas flows, and infer that their galaxy was interacting with another. For them, the merger would be an object of study, not an experience. They had reached the same conclusion astronomers reach today. The process is real. It is ongoing. It is calm. This experiential view reinforces everything learned so far. Galaxies collide without touching, not only in a physical sense, but in an experiential one. The collision does not intrude on daily reality. It does not disrupt local order. It unfolds in a realm of scale that exists far beyond immediate perception. By bridging physical processes with lived experience, the merger becomes less intimidating and more comprehensible. It is not a cosmic disaster unfolding overhead. It is a slow rearrangement of distant structure, happening quietly while life, wherever it exists, carries on. The night sky would change, but only enough to reward patience. Over immense spans of time, it would become a record of motion, a map of gravity's work written in light. For any single observer, it would remain familiar, stable, and reassuringly calm. In that sense, the universe is kind. Even when entire galaxies pass through one another, it allows those inside them to live undisturbed, gazing up at a sky that changes just slowly enough to feel eternal. By the time a single merger has run its course, it becomes clear that these events are more than curiosities. They are not rare accidents scattered randomly through cosmic history. They are fundamental processes that shape how the universe looks, how galaxies grow, and how structure emerges on the larger scales. Galactic mergers are not side effects of cosmic evolution. They are one of its main engines. At the most basic level, mergers explain how galaxies change over time. A galaxy is not born in its final form. It grows, accretes, reshapes, and settles through a long sequence of interactions. Small galaxies are drawn into larger ones. Comparable systems merge and lose their original identities. Over billions of years, this gradual assembly builds the diversity of galaxies seen today. This process is often described as hierarchical growth. In the early universe, matter was distributed unevenly. Slight variations in density, amplified by gravity, caused matter to clump. Small structures formed first. Over time, these structures attracted more matter and merged with one another, creating progressively larger systems. Galaxies grew by swallowing smaller neighbors and by merging with peers. In this context, a galactic merger is not an isolated drama. It is a step in a long construction process. This helps explain why galaxies in the distant universe often look different from those nearby. Observations show that early galaxies were smaller, more irregular, and more actively forming stars. As time passed and mergers accumulated, galaxies became larger and more structured. Many settled into calmer states after exhausting or heating their gas through repeated interactions. Mergers also help explain the variety of galaxy shapes. Spiral galaxies tend to dominate quieter environments where interactions are infrequent. Elliptical galaxies are more common in dense regions such as galaxy clusters, where mergers happen often. This pattern is not coincidental. It reflects the cumulative effect of interactions shaping structure over time. In other words, where a galaxy lives influences what it becomes. On even larger scales, mergers connect individual galaxies to the architecture of the universe itself. Galaxies are not scattered randomly through space. They trace vast filaments of matter stretching across hundreds of millions of light years, separated by enormous voids. This cosmic web emerged from the same gravitational processes that drive mergers, operating across scales far beyond individual galaxies. Cosmological simulations play a crucial role in understanding this connection. When scientists model the evolution of the universe using known physical laws, they begin with simple initial conditions. Tiny variations in density are allowed to evolve under gravity. Over time, matter flows along filaments, collects at intersections, and forms halos where galaxies are born. These halos merge, cluster, and grow, producing structures that closely resemble what telescopes observe. In these simulations, galactic mergers are not optional features. They are unavoidable outcomes of gravity acting over time. A central framework guiding these models is known as the lambda cold dark matter model. Written out in words, this describes a universe dominated by cold dark matter, which clumps and provides gravitational structure and dark energy, represented by the cosmological constant, which influences the expansion of space. Within this framework, galaxies form inside dark matter halos that grow and merge hierarchically. Mergers are therefore embedded in the deepest level of cosmological theory. This perspective elevates galactic collisions from individual events to universal mechanisms. They are how matter moves from small scales to large ones. They are how complexity emerges from simplicity. They are how the universe builds structure without needing sudden or violent processes. The same principles apply whether considering two dwarf galaxies merging in isolation or massive clusters assembling over billions of years. Scale changes, behavior does not. There is also an important lesson here about efficiency. The universe does not require precision engineering to create order. It relies on repetition. Simple rules applied over long periods produce intricate results. Gravity pulls, matter responds, mergers follow. Over time, structure emerges. This efficiency is visible in how consistently simulations reproduce real observations. When models include gravity, dark matter, gas dynamics, and star formation feedback, the resulting virtual universes develop galaxies that look strikingly like those seen through telescopes. Spiral arms, elliptical systems, clusters, and filaments all appear naturally. Nothing extra needs to be added. This success suggests that mergers are not anomalies needing explanation. They are expected outcomes of the universe's basic ingredients. There is also a deeper conceptual shift that mergers encourage. They push against the idea of galaxies as isolated objects. Instead, galaxies become chapters in a larger story, constantly influenced by their surroundings. Boundaries blur, histories overlap. A galaxy's present appearance reflects not only its internal processes, but the sum of its past encounters. Every merger leaves traces, whether in stellar motion, chemical composition, or large-scale structure. To understand a galaxy fully is to understand its interaction history. This has practical consequences for astronomy. When astronomers interpret observations, they must consider mergers as ongoing influences rather than completed events. Features such as tidal streams, stellar shells, or unusual motion patterns often signal past interactions. These features provide clues about mass distribution, dark matter structure, and the galaxy's evolutionary path. Mergers become tools for probing invisible components of the universe. By studying how galaxies respond to interactions, scientists can infer the properties of dark matter halos, test gravitational models, and refine simulations. In this way, mergers serve as natural experiments conducted by the universe itself. There is gentle irony here. The calmest collisions teach the most dramatic lessons. Galactic mergers reveal that change does not require impact. They show that emptiness does not imply isolation. They demonstrate how structure can arise from patience rather than force. This lesson extends beyond galaxies. The same hierarchical principles apply to clusters of galaxies, to the formation of large-scale filaments, and even to the distribution of matter across the observable universe. Small differences grow, structures merge, complexity increases. From this vantage point, a single merger becomes a window into everything else. Understanding mergers helps explain why the universe looks the way it does today. It clarifies why galaxies are arranged in patterns rather than scattered evenly. It reveals why some systems are active while others are quiet. It ties together local processes with cosmic architecture. Perhaps most importantly, mergers remind us that evolution at cosmic scales is neither chaotic nor violent by default. It is structured, rule-driven, and deeply consistent. The universe does not lurch from one state to another. It flows. By expanding the view from individual galactic encounters to universal patterns, mergers take on a new role. They are no longer endpoints or spectacles. They are mechanisms, operating quietly but persistently, shaping everything from the smallest galaxies to the largest structures known. In this way, galactic mergers teach a broader lesson about the universe itself. The most powerful forces often work slowly. The most significant changes often leave no obvious scars. And the largest structures of all are built not through sudden events, but through countless gentle interactions accumulating over time. Seen through this lens, the collision of galaxies without touching is not an oddity. It is the universe behaving exactly as it always has, building complexity from simplicity, one merger at a time. The word violence carries weight. It implies force, harm, suddenness, and loss. It belongs to a human scale, shaped by bodies that break and environments that change quickly. When it is applied to the universe, especially to events like galactic mergers, it brings those expectations along with it. This is where language begins to mislead. In astronomy, phrases such as violent merger, cosmic crash, or galactic smash are often used to capture attention. They are vivid. They are memorable. But they quietly import assumptions that do not belong at cosmic scales. They suggest impacts where there are none, destruction where there is mostly rearrangement, and urgency where there is only patience. The universe does not behave violently in the way the word implies. At human scales, violence is defined by speed. Things happen faster than systems can respond. Energy is transferred suddenly. Structures fail. At galactic scales, nothing happens quickly. Change unfolds over hundreds of millions or billions of years. Matter has time to adjust. Energy is redistributed gradually. Structures bend instead of breaking. Using the same word for both creates confusion. Metaphors are useful tools in science communication, but they have limits. They work best when the scale of comparison is similar. When the scale difference becomes extreme, metaphors begin to distort rather than clarify. A galactic merger compared to a car crash is not just inaccurate. It actively teaches the wrong intuition. A car crash involves rigid objects, short distances, and rapid energy release. A galactic merger involves diffuse systems, enormous separations, and slow gravitational evolution. The processes share a word but not a mechanism. Even the term collision is borrowed language. It persists because it is convenient, not because it is precise. In physics, collision can mean interaction rather than contact. But outside that context, the word carries a strong implication of impact. Without careful framing, it invites misunderstanding. This is why so many people imagine stars smashing together during mergers, or planets being flung violently into space. These images are not derived from physics. They are derived from metaphor. The problem is not that metaphors exist. It is that they are rarely unpacked. When science communication leans too heavily on dramatic language, it creates a gap between what is said and what is meant. That gap can lead to surprise, confusion, or distrust when the true explanation turns out to be calmer than expected. The universe feels less intuitive not because it is inherently strange, but because it has been described using inappropriate analogies. Calm processes described with violent language create false tension. There is also a subtle psychological effect at work. Words like violent and catastrophic imply danger. They suggest threat and urgency. When applied to distant cosmic events, they can trigger unease that is not supported by the underlying science. The result is a mismatch between emotional response and physical reality. In truth, galactic mergers are among the most orderly large-scale processes in the universe. They follow predictable rules. They can be modeled accurately. Their outcomes are consistent across a wide range of conditions. Nothing about them is chaotic in the everyday sense. This does not mean they are uninteresting. Quite the opposite. Their interest lies in their restraint. The universe does not rely on forceful resets to evolve. It relies on accumulation. Gravity applies small influences repeatedly. Over time, those influences add up. Structure changes, but it changes smoothly. This is a far more subtle story than the language of violence allows. There is also a historical reason these words persist. Early astronomy lacked the data and simulations available today. Observations were limited to static images. Without motion or timescale, distorted galaxies looked broken. The natural assumption was that something dramatic had occurred. As understanding improved, the language remained. Once a term becomes common, it is difficult to replace. Violent merger sounds compelling. Gentle gravitational restructuring does not fit neatly into a headline. Yet accuracy matters, especially when the goal is understanding rather than excitement. Scientists themselves are aware of this tension. In technical contexts, descriptions are careful and precise. In public-facing context, language often shifts toward metaphor. This is understandable, but it comes with responsibility. Metaphors should illuminate, not dominate. One way to correct this is to shift focus from events to processes. A merger is not a moment. It is a sequence. It begins before anything looks unusual and continues long after visible features fade. Framing it as a process immediately removes the expectation of impact. Another way is to emphasize time scale. Violence is associated with speed. Slowness undermines the metaphor naturally. When listeners understand that a merger unfolds over billions of years, the idea of violence loses its footing. Precision in language also invites curiosity rather than fear. Describing a merger as a redistribution of orbits, a reshaping of gravitational potential, or a period of enhanced star formation may sound technical, but these phrases carry fewer misleading assumptions. They encourage questions instead of reactions. There is room for gentle humor here as well. Calling something violent that takes longer than most stars live stretches the meaning of the word beyond usefulness. If anything, galactic mergers are exercises in extreme patience. The universe waits. Aligning tone, language, and reality is not about removing wonder. It is about relocating it. The wonder of galactic mergers lies not in imagined explosions, but in the fact that enormous systems can pass through one another, transform, and settle without disruption. It lies in the idea that emptiness allows complexity. It lies in the fact that gravity, acting alone, can reorganize hundreds of billions of stars without ever needing them to touch. When language reflects this, understanding deepens. This also respects the listener. It trusts that curiosity does not require alarm, that interest does not depend on exaggeration, that calm explanation can be more engaging than spectacle. By stepping away from violent metaphors, the story of galactic mergers becomes clearer and more coherent. The earlier ideas about emptiness, gravity, time, gas dynamics, and structure all fit together naturally. Nothing feels contradictory. Nothing needs to be softened or walked back. The universe emerges as it is, vast, patient, and quietly active. Words shape expectation. Expectation shapes interpretation. When those are aligned with reality, learning becomes easier and more satisfying. Violence is the wrong word, not because galaxies are gentle in a sentimental sense, but because the physics does not support it. The processes involved do not match the meaning we assign to that term. Continuing to use it obscures more than it reveals. Choosing calmer language is not an aesthetic preference, it is an act of accuracy. In the end, galactic mergers are not stories of destruction. They are stories of motion, influence, and long-term change. Describing them honestly allows their true nature to emerge, one that is far more interesting than any imagined crash. The universe does not shout when it changes. It rearranges itself quietly, leaving behind patterns that reward careful attention rather than dramatic interpretation. When the language matches that reality, the story finally sounds like the universe itself. When the story of galactic collisions is taken as a whole, a different picture of the universe comes into focus. Not a place of constant impact or sudden catastrophe, but a place defined by motion, patience, and subtle influence. Galaxies change, but they do so quietly, guided by forces that act across immense distances and over extraordinary spans of time. The paradox at the heart of this story remains simple and true. Galaxies collide without touching. What initially sounds impossible becomes inevitable once scale, emptiness, and gravity are allowed to take their proper roles. Space dominates everything. Stars are brilliant, but they occupy almost none of the volume of a galaxy. Between them stretches an ocean of emptiness so vast that even when two galaxies overlap, their stars pass by one another without contact. This emptiness is not a flaw in the universe's design. It is what makes gentle change possible. It allows motion without impact and interaction without destruction. Gravity provides the connection. Across this emptiness, gravity reaches effortlessly. It does not need contact. It does not require speed. It shapes motion slowly and persistently, drawing galaxies together long before they appear close and continuing its work long after they overlap. Through gravity, galaxies influence one another deeply without ever colliding in the everyday sense. Time completes the picture. Nothing about a galactic merger happens quickly. Each stage unfolds over hundreds of millions or billions of years. Orbits adjust little by little. Gas compresses, forms stars and disperses again. Structures stretch, warp, and relax. Change accumulates so gradually that it feels calm rather than violent. When galaxies approach, their dark matter halos meet first, forming an invisible framework that guides everything else. Stars follow altered paths. Gas responds more actively, colliding, compressing, and lighting up new generations of stars. These bright episodes are brief relative to the merger as a whole, flickers of creation in an otherwise steady process. As galaxies pass through one another, visual overlap creates the illusion of crowding. In reality, stars continue along smooth trajectories. Planetary systems remain stable, and the universe behaves with remarkable restraint. What looks like a crash is physically a passage. Distortion replaces destruction. Spiral arms stretch into tidal tails. Disks warp rather than shatter. Cores drift and settle. The galaxy changes shape, not because it has been damaged, but because it is responding flexibly to a new gravitational environment. Over time, the original structure fades, replaced by a smoother, more relaxed form. Star formation rises and falls in response to compressed gas, adding light and complexity without threatening stability. Central black holes move inward slowly, sometimes forming pairs that may take billions of years to merge, releasing their energy not as fire or impact, but as faint ripples in space itself. Even the most extreme components follow the same calm rules. When the process finally resolves, two galaxies become one, not through conquest or collapse, but through blending. The system settles into equilibrium, carrying the combined history of both parents. The universe does not mark the moment, it simply continues. From the inside, almost nothing feels different. Observers within a merging galaxy would see the night sky change so slowly that it would seem eternal. Life, if it exists, would continue uninterrupted. The largest rearrangements in the universe would remain background processes, unfolding far beyond immediate experience. This perspective reshapes how galactic mergers are understood. They are not violent events punctuating an otherwise stable universe. They are one of the ways the universe evolves continuously. Through mergers, galaxies grow, transform, and redistribute matter. Through them, structure emerges on scales far larger than any individual system. Cosmological models that describe the universe's evolution rely on these processes. They show matter flowing along filaments, gathering into halos, merging and settling again and again. Galactic collisions are not exceptions to the universe's behavior. They are expressions of it. Language matters here. When mergers are described as violent or catastrophic, the underlying reality becomes harder to see. Those words impose human expectations on processes that do not share human scale or speed. Reframing mergers as quiet, gravitational interactions aligns description with physics and restores coherence to the story. The universe is dynamic, but not frantic. Motion does not require impact. Change does not require destruction. Complexity does not require chaos. These ideas run counter to everyday intuition, yet they describe the cosmos accurately. There is a subtle elegance in this. The same force that keeps planets in orbit can guide entire galaxies through one another without harm. The same emptiness that makes space feel lonely enables vast systems to interact gently. The same time that erodes mountains allows galaxies to reshape themselves patiently. Taken together, these truths resolve the opening paradox. Galaxies collide without touching, because touching is not how change happens at this scale. Influence replaces impact. Reshaping replaces breaking. Motion replaces violence. This understanding does not close the story of galactic mergers. There is always more detail to uncover, more variation to explore, more connections to trace between small scales and large ones. But it does bring clarity. The universe is not a place of constant crashes, it is a place of quiet motion. Galaxies drift, meet, pass through and merge, guided by gravity and time. They change form, light up briefly with new stars and settle again. All of this happens without urgency, without contact and without spectacle. In the end, the calmness is not an absence of activity, it is the result of balance. A universe spacious enough, patient enough, and governed by simple rules applied endlessly. When galaxies collide without touching, they reveal something profound about reality itself. The largest changes do not announce themselves. They unfold quietly, carried forward by forces that do not hurry and do not need to. The universe remains in motion, always evolving, yet doing so with remarkable restraint. Collisions without contact sound like a contradiction, only because everyday experience trains the mind to expect impact whenever change occurs. At human scale, objects meet, press, strike, and break. Motion is resolved through touch, but the universe does not share those assumptions. At the scale of galaxies, change unfolds through distance rather than contact, through influence rather than force. Galaxies collide through gravity. This simple statement resolves the paradox at the heart of everything explored so far. When galaxies approach one another, their stars do not smash together. Their planets are not torn from their orbits. Their structures are not shattered by sudden blows. Instead, gravity reaches across vast emptiness, gently reshaping motion over immense spans of time. Space makes this possible. Stars occupy almost none of the volume of a galaxy. Between them lies an expanse so large that even when two galaxies overlap, their stars pass by without contact. The visual brightness of a galaxy hides how sparse it truly is. Light suggests solidity, but reality is dominated by emptiness. That emptiness is not a void of inactivity. It is the medium that allows motion to remain calm. Gravity provides continuity. Across that emptiness, gravity acts patiently. It does not need to rush. It does not need to strike. It alters paths slowly, bending orbits, redistributing energy, guiding systems into new configurations without ever requiring physical contact. What looks like a collision is, in truth, a long conversation carried out through gravitational influence. Time completes the picture. Galactic interactions unfold over hundreds of millions to billions of years. Nothing happens quickly enough to feel violent. Change accumulates gently. Structures stretch rather than snap. Gas compresses and forms new stars, then disperses again. Even the most dramatic transformations are spread across timescales so long that they feel like stillness. This combination of space, gravity, and time produces a universe that is dynamic without being destructive. Galaxies pass through one another because they can. They change because gravity demands it. They survive because the universe allows them the time and room to adjust. Human intuition struggles with this because it is shaped by speed and proximity. A car crash, a falling object, a storm. These events teach that force comes suddenly and leaves obvious damage. When those instincts are applied to cosmic scales, misunderstanding follows. The universe does not operate by the same rhythms. Understanding galactic mergers requires letting go of urgency. There is no single moment when one galaxy becomes another. There is no instant of impact to point to. The beginning is subtle. The ending is gradual. In between lies a long period of adjustment during which stars, gas, and dark matter respond to a shared gravitational environment. Even creation emerges quietly. Star formation increases during mergers not because stars collide, but because gas compresses gently enough for gravity to take over. New stars light up the galaxy without threatening its stability. The process is creative rather than destructive, and even that creativity is temporary, balanced by feedback that restores calm. At the centers of galaxies, black holes approach one another slowly, often taking longer to merge than the galaxies themselves. Their influence remains local. Their final union, if it occurs, releases energy not as light or shock, but as faint ripples in space itself. Even here, restraint dominates. From inside a galaxy, almost nothing feels different. The night sky changes slowly, generation by generation. Life, if it exists, continues uninterrupted. The largest rearrangements in the universe take place far beyond immediate experience, unfolding quietly while local systems remain stable. This perspective brings relief. The universe is not fragile. It does not require constant repair. It does not collapse when its largest structures interact. Instead, it evolves through processes that are inherently stable because they are slow and distributed. Collisions without contact are not exceptions. They are the rule. Galaxies grow by merging. Clusters form by accumulation. The large-scale structure of the universe emerges through countless gentle interactions layered over deep time. This is not chaos disguised as order. It is order expressed through patience. Language matters in understanding this. When galactic mergers are framed as violent or catastrophic, they feel threatening and confusing. When they are framed accurately, as gravitational reshaping events unfolding across vast timescales, they become coherent and even calming. The universe reveals itself as a place where change does not require drama. There is quiet elegance in that idea. The same force that holds a planet in orbit can guide entire galaxies through one another without harm. The same emptiness that makes space feel isolating enables the universe to change gently. The same time that erodes mountains allows galaxies to evolve without ever needing to touch. Seen this way, the cosmos feels less hostile and more comprehensible. Galaxies collide without touching, not because something unusual prevents contact, but because contact is unnecessary. Influence replaces impact. Motion replaces force. Transformation replaces destruction. This understanding does not diminish the wonder of the universe. It deepens it. The universe does not rely on spectacle to achieve complexity. It relies on consistency. Simple rule applied endlessly produce structures of extraordinary richness. The listener can rest comfortably within this picture. The universe is active, but it is not in a hurry. It is changing, but it is not breaking. Even its largest events unfold with remarkable calm. Collisions without contact are not a trick of language. They are a reminder that reality operates on scales far removed from intuition, and that when those scales are respected, the universe reveals itself as a place of quiet motion rather than constant violence. Galaxies drift. Gravity guides, time smooths, and within that vast patient process everything continues.